Good afternoon. Today we will see the flow through pipe remaining points. First is pipe in series. In this diagram you can see there are two tanks which are connected by three different pipes. When the pipes of different length and diameters are connected to each other to form a pipeline, then such a pipeline is called as a compound pipe or pipes in series. As the pipes are in series, the discharge through each pipe will be same. Q is equal to A1V1 is equal to A2V2 is equal to A3V3. Considering all the losses, means there is one pipe which has a diameter D1, length L1 and coefficient of friction F1, where V1 is the velocity. Similarly for other pipe L2, D2, F2, V2 and L3, D3, V3 and F3. A is the tank which is at a distance or which is at a head H from B. Now considering all the losses, total loss of head is equal to major losses plus minor losses. So H is equal to HL1 plus HL2. Major losses are nothing but head loss due to friction in each pipe. HL1 is equal to HF1 plus HF2 plus HF3, which is equal to 4F1 L1 V1 square upon 2 GD1. Similarly for other two pipes. Minor losses are equal to entrance loss, contraction loss, expansion loss and exit loss. So FL2 is equal to 0.5 V1 square by 2G plus 0.5 V2 square by 2G plus V2 minus V3 bracket square by 2G plus V3 square by 2G. These are the minor losses. If minor losses are neglected, then total loss of head is equal to major loss, which is nothing but 4 by 2G and remaining terms as it is, or this equation is representing the total loss. If discharge through pipe is given, then above equation will change to this. These all are about when pipes are connected in series. Now we will see when we connect the pipes in parallel. Here is the example. When pipe is divided into two or more parallel pipes which again join together at a downstream as shown in figure, then pipe is said to be a parallel. Here is one pipe, it is getting divided into two pipes and again the pipe is coming back to the original. So discharge is going to divide into two pipes Q1 and Q2. So in other words we can say Q is equal to Q1 plus Q2. In order to increase the discharge passing through main pipe, the pipes are connected in parallel. The discharge in main pipe is equal to sum of discharge in each of the parallel pipes. So as I said before, Q is equal to Q1 plus Q2. When the pipes are arranged in parallel, the loss of head in each pipe is same. This sentence is important. When the pipes are arranged in parallel, the loss of head in each parallel pipe is same. Means whatever loss of head is happening in each parallel pipe will be same. So HF1 is equal to HF2. So this is the concept of pipes connected in parallel. Let's see the next concept of equivalent pipe. A compound pipe which consists of several pipes of different lengths and diameter to be replaced by a pipe of uniform diameter and the same length as that of compound pipe is called as equivalent pipe. The uniform diameter of equivalent pipe is called as equivalent diameter. Equivalent pipe is a single pipe of uniform diameter whose discharge and loss of head are same as that of a compound pipe. Therefore, for equivalent pipe, the head loss in equivalent pipe is equal to head loss in pipe 1, head loss in pipe 2 plus head loss in pipe 3. Means suppose there are three pipes, one is of this diameter, another is of this diameter and another is of this diameter, D1, D2 and D3. The lengths are L1, L2 and L3. We have to construct a single pipe which has length equal to L1 plus L2 plus L3 is equal to L and it has constant diameter D, and it should have discharge and loss of head same to the compound pipe. Such a pipe is known as a equivalent pipe. So here HE is equal to HF1 plus HF2 plus HF3. So 4 FL V square upon 2 GD, which is equal to 4 F1 L1 V1 square upon 2 GD1. Similarly for other two pipes. If suppose coefficient of friction is same and discharge is equal to Q is equal to A1 V1 is equal to A2 V2 is equal to A3 V3 is equal to pi by 4 D1 square V1, pi by 4 D2 square V2, which is equal to pi by 4 D3 square V3. So V1, V2, V3 values we have got. Put these values of V1, V2, V3 in the above equation. So we will get H is equal to 4FL into 4Q pi D1 square bracket square and all other terms. Doing the simplification, what you will get 4FL V square upon 2GD is equal to taking all the common terms, where V is equal to Q by A is nothing but 4Q upon pi D square. In the equation of H we have replaced V. So rewriting the equation, this term and this term both are same and we can cancel it, and we will get L upon D raised to 5 is equal to L1 upon D1 raised to 5 plus L2 upon D2 raised to 5 plus L3 upon D3 raised to 5. This is known as Dupuit's equation, which may be used to determine the size of equivalent diameter. Means in this equation we know L1, L2, L3, we know D1, D2, D3, and L1 plus L2 plus L3 is nothing but L. Only remaining is D, and this diameter can be calculated by using Dupuit's equation, and this diameter is nothing but equivalent diameter. So length of equivalent pipe is L is equal to L1 plus L2 plus L3. So this is all about the equivalent pipe. You have to remember this Dupuit's equation. Next we will see Colebrook's equation for commercial pipe. The friction factor in fully developed turbulent flow depends on the Reynolds number and the relative roughness epsilon by D, which is the ratio of mean height of roughness of a pipe in the pipe diameter. The functional form of this dependence cannot be obtained from theoretical analysis, and all available results are obtained from the plane tasking experiments using artificially roughness surface, usually by gluing sand grains of known size on the inner surface of a pipe. The friction factor was calculated from measurements of the flow and the pressure drop. The experimental results obtained are presented in tabular, graphical and functional norms obtained by curve-fitting experimental data. In 1939, Colebrook combined the available data for transition and turbulent flow in smooth as well as rough pipes into the following implicit relation known as Colebrook equation. This is the Colebrook equation. 1 upon under root F is equal to minus 2.0 log epsilon by D divided by 3.7 plus 2.51 Re into under root F. It is for turbulent flow. This is accepted design formula for turbulent friction. It was plotted in 1944 by Moody into what is now called the Moody chart for pipe friction. The Moody chart is probably the most famous and useful figure in fluid mechanics. It is accurate to plus minus 15% for design calculation over the full range. It can be used for circular and non-circular pipes flows and for open channel flows. The equation is used to evaluate for friction factor if Reynolds number is known. The Colebrook equation is implicit in F, means F is here also present and here also present, and thus the determination of the friction factor requires some iteration unless an equation solver such as EES is used. By using some equation solver, we have to find out the value of under root F. So that is found after some iteration. 1 by under root F is approximately equal to minus 1.8 log 6.9 Re plus epsilon by D divided by 3.7 raised to 1.11. The value of epsilon by d can be calculated by using these standard charts. Roughness value epsilon is given in this table, and we know the diameter as well as we know the Reynolds number, and by using this we can calculate the friction factor mathematically. By using Moody chart we can also calculate the friction factor. In next point we will see how to read the Moody chart. The primary purpose is to provide graphical representation of Colebrook's equation. Before inexpensive computers become widely available, it provided means of quickly estimating the Darcy's friction factor F. The Moody chart shows the value of friction factor as a function of Reynolds number for various number of relative roughnesses. Note that both x and y axis use the log scale. If Reynolds number of a flow is below approximately 2000, the F is a only function of Reynolds number, and it can be calculated directly from the formula 64 over the Reynolds number. This formula is represented graphically by a line on the left side of a Moody chart. If the Reynolds number is in between approximately 2000 and 4000, the flow is transition region, and there is no accurate method of determining the friction factor for this range of Reynolds number. Most of the Moody chart is dedicated to the turbulent flow region, in which Reynolds number is greater than 4000. From Colebrook's equation, we know that friction factor for turbulent flow is a function of both Reynolds number and relative roughness. The only way to plot a function of two variables on the two-dimensional graph is to hold one variable constant for varying other. In case of Moody chart, Reynolds number is varied by holding the value of the relative roughness constant. For example, suppose the pipe you are examining has relative roughness of 0.002. You will use the curve shown in the orange line determining the value of a friction factor at different Reynolds number. Now suppose Reynolds number of a flow is 10,000. Draw a vertical line from 10,000 on the x-axis until it reaches the orange line. Now draw the horizontal line from the intersecting point to the y-axis and read the friction factor. For this example, the friction factor is approximately 0.03.